All right, so the beauty of this equilibrium and master degree of freedom concept is that when you follow this path, you don't really need to wonder if your system is statically determinate or statically indeterminate. So I know that as long as we were doing just one bar in axial loading, it's really easy to figure out if something is determinate or indeterminate. Like for instance, if I give you a structure like that in which I have a series of bars stuck between two walls, you already know this is going to be a statically indeterminate problem because I have too many reactions, and I can now, for instance, find the solution to what reaction I have at wall A or wall D simply based on equilibrium. So we know this is a statically indeterminate problem, and we know we're going to have to find a solution combining equilibrium, constitutive, and compatibility. But this is typically a decision that you have to do ahead of time if you want to choose something like the force method, because so far we have been using force method to solve statically indeterminate structure, and you start doing this only once you have recognized that the structure is statically indeterminate. So when we start having systems with more bars, more constraints, and so on, sometimes cannot be obvious to you if the structure is statically determinate or indeterminate. And so the good thing of using this equilibrium and master degree of freedom concept is that you start doing your work and you work along the path, and automatically as you work along, you're going to figure out if it's determinate or indeterminate, and whatever it is, either way, you're going to find your way to the solution. So traditionally, if you have a simple system like this with 3 bars in series between walls, the most straightforward way to solve this problem is to use the force method. So what do we do when we do the force method, and why is it called the force method? It's called the force method because the procedure is that we go from the statically indeterminate system to the companion statically determinate problem by removing the redundant support. So we say, let's get rid of this extra wall. So that wall was giving me a redundant reaction Rxd, and then I solve this whole problem and I find what is the displacement at the redundant support, uxd, in terms of the redundant reaction. So my uxd is going to be equal to the sum of the elongation of the 3 bars, delta 1 plus delta 2 plus delta 3. And the idea is that we obtain these elongations in terms of the applied loading and the redundant reaction, and then we say, but remember there was a wall at D, so uxd must be 0. So if I write uxd in terms of these forces, I'm going to find that uxd is going to be equal to rxd plus q minus p. You can do this calculation a little more leisurely on your own. This is stuff we have done before. But if I do all the algebra, I can do it in my head. It's a simple system. I'm going to have the elongation of this thing is rxd plus q minus p divided by k1, plus the elongation of bar 2 is going to be rxd plus q divided by k2, and the elongation of bar 3 is going to be simply equal to rxd divided by k3. And by the way, k1, k2, and k3, assume I've given them to you. The stiffness of each segment of the bar in terms of the area of the bar, modulus of the material, length of this segment of the bar. So if you do something like, if you have given you all this work, I've done all that work for you, then to find the displacement at D, the sum of the elongations, is very easy. This is the relationship. And then you say, but all this must be equal to 0. And then out of this, you find the unknown redundant reaction Rxd, and then you have to back substitute to find all the solution. So this is called the force method, because the idea is that your extra known is a force, and you find this force by plugging it into a compatibility constraint. So that's the force method. When we use this other idea over here of equilibrium and master degree of freedom, we follow a path for solving the static and indeterminate structure, which is called the displacement method. So this is called the displacement method for the same reason that that's called the force method. In the force method, my unknown is the extra force, the redundant reaction at one of the walls. In the displacement method, my main unknown are displacements. So which displacement? The master degrees of freedom of the system. So if I look at this system here, what are the master degrees of freedom of the system? So in this one, you have to use a little bit, you have to put on your thinking hat, because there are no blocks here, right? So I didn't draw the blocks, so what is the displacement of the blocks? But you do not need to have actually blocks in your structure to use this technique. You can say, well, in a way, section B is my block. Again, if you want, again, imagine a tiny block here on section B like that, with wheels. It doesn't change anything if I put it there or not. The reality is that, again, what I'm interested in is the displacement at the section where the force is applied. So if I put a block there, then I have something that look like those diagrams that we did for equilibrium and compatibility. But I don't need to put the blocks in. I can put a block here and a block here. And then if I put a block here and a block here, then you would have realized, oh yes, what controls everything in the solution of the problem is how much these blocks displace. Because if I know how much each of these blocks displace, then the elongation of the bar is fixed by that, by elongation of the bar, the strain, the stresses, and so on. So the bottom line is the section where the forces are applied are the same as if they were the block. And my master degrees of freedom of this system are the displacement at the ends of the bars, the displacement at this section which connects the bars. So if this is section C, I'm going to have at this section a displacement UC, and for section B here, I'm going to have a displacement UB for section B. And I'm drawing them that way because, again, I'm assuming that my x-axis goes that way. So the displacement of those two sections are my master degrees of freedom of the system. So the first thing that you have to do, step 0 if you want, is figure out what is the master degree of freedom of the system. So what are the master degrees of freedom of the system? It can be more than one. So for instance, in this case, my master degrees of freedom are Ux of section B and Ux of section C. I have two master degrees of freedom, UXB and UXC. So what do I need to do now? I need to do my first step, which is write the conjugate equilibrium equation. Conjugate equilibrium equation. So what are the conjugate equilibrium equation? If I'm looking for the displacement in the x direction of section B, what is conjugate to the displacement in the x direction of section B is that of all the position that section B can take, is going to take the position for which section B is in equilibrium. So the conjugate to this displacement is going to be a condition in which the sum of the forces in the x direction on section B must be 0. And the conjugate to that, whichever position C is going to take the position such that section C is in equilibrium. So my conjugate equilibrium equation is that sum of the forces x on section C must be 0. So these are my two equilibrium equations. So how do I write this equilibrium equation? How do I impose equilibrium? Well, in order to impose equilibrium, I have to do my standard trick of doing my isolation bubble. So I'm going to isolate section B, and then I'm going to isolate section C, and I'm going to create two free body diagrams, one free body diagram to do this and one free body diagram to do that. And so if I look at my first bubble, which is a bubble around section B, and by the way, when I do section B, I do not cut through the wall. So at this point, I just drew the block so that you can reconnect to what we have done before. But there are no blocks in this problem. It's just a section. So I do a bubble around the section that I want to put in equilibrium. So if I do a bubble around that section, I get something that looks like that. I cut through the first bar, and then I cut through the second bar, like that, around the section. And this is the section on which the force is applied. This is where force P is applied, right at this point, this section here, P, applied at that section here. So this is section B. Oh, too many chalks, B. And then out of the cut section here comes the force in bar 1 and 1. And out of the cut on the second bar comes the force in bar 2 and 2. So this is the free body diagram to do that equation here. So how does that come out? Sum of the forces x equals 0. X goes that way. So I have N2 minus P minus N1 equal to 0. That's my first equation. Then I do the free body diagram that corresponds to that bubble over there. So that bubble has a little chunk of bar 3. It has a little chunk of bar 2. This is my section C. Oops. This is my section C. On section C, I have force Q applied that way. I have the internal force resultant in bar 3. I have the internal force resultant in bar 2. And so I can write my equilibrium equation as sum of the forces in the x direction on section C equals 0. That's going to give me N3 plus Q minus N2 equal to 0. So these two are the equilibrium equation. So these are my master equilibrium equation. Okay? Master equilibrium equations. And once I write these equations, this is the moment in which I ask myself, is the system statically determinate or statically indeterminate? How do I find that out? It's very, very simple. At this point, after I wrote the master equilibrium equations, conjugate to the master degrees of freedom, I count equations. So I have two equations. And these equations are written in terms of internal force resultants, right? Are written in terms of N1, N2, and N3. So now you count the equation, number of equations, and you count the number of unknown internal force resultant N. So you have N1, N2, N3. You have 3 unknowns. So you have a number of equations which is less than the number of unknown, which means you cannot solve this system of equations for the unknown force resultant. This is the equilibrium equation, and by doing static equilibrium alone, you cannot solve the system. So static equilibrium alone is not enough to solve the problem, which means the problem is statically indeterminate. Now, the beauty of this approach is that once you find that the problem is statically indeterminate, you don't need to scrap all of this and start away again using the force method. Once you have done this thing, you say, okay, so that's fine. It just means that I have to write this equilibrium equation in terms of my master unknowns, which are the displacement UB and UC. Because you have two equations, and if you can write it in terms of these two unknowns, you can solve the system. So how do you do that? You do the next two steps we said before. So the second step is to write N delta relationships. So the N delta relationships in this case are very easy because it's elastic and I give you the stiffness, so it doesn't get much easier. So my step 2 is simply going to be that N1 is equal to K1 delta 1, N2 is K2 delta 2, N3 is K3 delta 3, and kaboom, you're done with the N delta relationships. So the second step for linear elastic bars, which I give you the stiffness, is very, very easy. The third step, we already did it when we were doing compatibility. The third step is what are the relationship between the elongation of the bar and the master degrees of freedom. We did this before. So what is the elongation of bar 1 in terms of the displacement of the sections? The elongation of bar 1 is going to be UB minus 0. So I can write delta 1 is equal to displacement at the end of the bar minus the displacement at the beginning of the bar. Delta 2, the elongation of bar 2, is the displacement at the end of the bar, which is UC, minus the displacement at the beginning of the bar. So I can write that delta 2 is equal to UC minus UB. and the elongation of bar 3 is the displacement at the end of the bar, which is 0, minus the displacement at the beginning of the bar. So delta 3 is 0 minus UC. So this is my third set of equations. So what do I do now? I take the 3 equations, I put them into the 2 equation, and then I put them into my equilibrium equation number 1. So that's the path that we're going to solve to do the displacement method. So I'm going to land here. So I'm going to rewrite this equation here in terms of u's. So what it says, so that's the same 2 equations that I had up there. I'm going to rewrite them down here in terms of the displacement. So N2 is K2 delta 2. Delta 2 is UC minus UB. So instead of N2, I write K2 that multiplies delta 2, which is UC minus UB, minus P minus N1. N1 is K1 delta 1. Delta 1 is UB. So minus K1 UB equal to 0. And then I write N3. N3 is K3 delta 3. So K3 times delta 3, which is 0 minus UC, so is UC with a minus in front of it, plus Q minus N2. N2 is K2 delta 2, so minus K2, and delta 2 again is UC minus UB, equal to 0. These are the same equations of this equation here, but now they are written in terms of UC and UB. Only 2 unknowns. Beautiful, right? Because now we have 2 equations in 2 unknowns. We can solve for UC and UB. And if you have UC and UB, you have the elongation. If you have the elongation, you have the strain. If you have the strain, you have the stresses, and so on. So why does this method always work? It always works because you always have a number of equations equal to the number of the unknown master degrees of freedom. That's why you do not care if the system is determinate or indeterminate. You do the equilibrium, the master equilibrium, look at it and say, can I solve? If you can solve it, you're done. You find the internal resultant. From there, you find everything. If you cannot solve, you do not throw up your arms in the air. You just do this step over here. You find K and delta. You get to the delta displacement relationship, and you recast this expression in terms of the unknown displacement, master degrees of freedom. That's why it's called the displacement method. It's beautiful. It always works. Okay? So one of the important things that now you guys have to learn is that you cannot just say there is one method, I turn the crank. There are many ways to put together these relationships, and depending on the problem, you may choose one method or the other one. These and these are totally equivalent methods in which you use the same relationships to get to the same answer. It's just a matter of conceptualizing the way to solve the problem in a different way. Okay? So get to work, do the next problems, and see how it goes.